start a new slide. Yeah. From this one, you know how to do repeated squaring. Yeah. You keep doing squaring operations. Yeah. Repeated squaring. Yeah. And later, I will post the first project soon. You need to write functions testing 3 algorithms. The first one, the brute force. Second one, repeated squaring. Third one, Horner's rule. Yeah. And then do comparisons. Yeah. Yeah. So now we have that repeated squaring. Yeah. And here you can see at the end of last time we compare how many multiplications we can save. Here we use this example when k equals 10, 2 to the 10th, yeah. N equals power of 2, 2 to the 10th. So n equals this number, 1024. Yeah. And for this monomial, repeated squaring, we only need to use 10 multiplications. If you use Horner's rule, you need 1023 multiplications. The difference is, you can see, so big. Yeah. But that's just for k equals 10. Think about, when k is a relatively large number, your save would be more than this one. Yeah. Here I also mention another related question. I posted our quiz number 1. Yeah, so most of you noticed that. In quiz 1, there is one question you need to connect to repeated squaring here. There is a question asking you if it's possible, then given a degree n polynomial. Oh, that one, you need to be very careful, okay? Yeah, that one. If you only use repeated squaring, still not enough. Yeah. So we need to complete the remaining 2 topics. Then you can answer that question well. Yeah. Because I saw some students already submitted the quiz. Yeah, a few students already submitted the quiz. Yeah. But we haven't completed. So we need to use the knowledge of the whole part C. We don't use part D. Yeah. We don't use part D, but we need to use knowledge from whole part C. Yeah. But several students already complete. Yeah. So do not wait until we finish the whole part C. Yeah. So then you can work, but you do not need to submit, right? No time limit. Just leave there, right? Do not submit. Yeah. Okay. For the quiz, you have lot of time. Yeah. All right. Yeah. Yeah. So here, then next, when we go to the next topic, yeah, look at my comments, my conclusion here, the essence of the method. Reuse the resource as much as we can to save operations. Yeah. CJ, two students join us, but you can admit from this side. All right. Yeah. So I want to make a few comments here on this conclusion. Yeah. Reuse the resource. Yeah. This point is very important because for this class, this algorithms class, what we are doing here, we want to design efficient algorithms, right? That's our goal. That's our main goal, design efficient algorithms. And how to make it? The basic idea is minimize the resource used. Minimize the resource used. What kind of resource we are talking about here? When I talk about resource, I mean two types of resource. We want to try our best to reduce. The first type, we call the primary type. Our primary resource, that's the computation resource. Okay? So when we talk about resource, there are two types. The first type, computation resource. This is the primary resource. Okay? The second type, storage resource. Memory storage space resource, that's also resource, but that resource is secondary. Yeah. Not as important as the primary resource, but also an important consideration. Okay, after you address the computation resource, next thing you need to think about if you can reduce as much as you can the memory storage resource. Yeah. So that's what we typically doing in this class. So next question, how to reduce computation resource? There is a general answer. There is a general answer for this question, reduce computation resource. Reuse your computation resource. Reuse. Okay? Yeah. Reuse as much as you can. That's the, general way we reduce the computation resource. Reuse. Yeah. So what's the meaning of reuse? Now I explain in the next slide. Next slide I will how to reuse your computation resource. Okay, all right. Yeah. If n is not any power of 2, the previous slide we did special case, power of 2. Then we just do the repeated squaring. But in general, n is not a power of 2. But we want to use repeated squaring technique to minimize the number of multiplications to save our computation resource. So how to do that? Here, let me use a simple example so you can see the idea easily. In this example, let's consider n equals 217. Not a power of 2. Okay? Yeah. So the first question, can we break it as a sum of power of 2? Sum of power of 2. So each term is a power of 2. Then we add up several powers of 2. Then we can still use the repeated squaring technique. Okay? Yeah. All right. What is the largest power of 2 under n? Below, less than or equal to n. First, we find that number, 128. 2 to the 7th. Because if you look at the 2 to the 8th, it is larger than this number. So you just take 2 to the 7th. Then you take this number out of n. Yeah. All right. For the next step, we want to prepare our computation. How to prepare it? The fastest way to get x to the 128. Let's calculate this monomial first. The power of 2. We can use repeated squaring. And we want to take the fastest way to find it. Keep doing squaring operations. And how many squaring operations you need to do based on what we learned last time? How many from last time? Power of 2. Number, give me number. How many? 7. 7. Exactly. 2 to the 7th. Then just take 7. That easy. That's straightforward. Okay? Yeah. All right. All right. 7. Yeah. Then. But when you find this intermediate result, this is intermediate result. It's not our final answer, right? That's the intermediate result. Okay? Yeah. So we need this one for our final answer. Okay? Yeah. For our final answer. All right. So we need to do some preparation. We need to prepare. We need to get ourselves ready to find the final answer. Yeah. So when we do preparation, we maintain a pool of our resource. Because those intermediate results could be useful in our calculation of the final answer. Intermediate results could be useful. Don't throw away. Okay? Keep, maintain, save your intermediate results as your resource. We treat that as our resource. Okay? So here, let's maintain that pool. Yeah. So this pool contains all these intermediate results. Okay? X squared, x to the 4th, x to the 8th, all, yeah, because when we get x to the 128th, we need to go through all these monomials with power of 2 exponents, right? Don't throw away. Yeah. We calculate these intermediate results. They could be useful in our future calculation, right? Yeah. So let's save them. Okay? Yeah. Put in a pool. Yeah. Because we want to reuse these resources later. So that's mean I talk about reuse the resource. Here we want to reuse the resource intermediate results here. Okay? All right. Next step. Now, decompose the number 217 as a sum of powers of 2. Okay? Yeah. First split, 217 equals 128 plus 89. Okay? So the first number already power of 2, but second number is not power of 2. So we need to split second number again and try to get the largest power of 2 less than or equal to 89. That's 64. Okay? So we take out 64 out. Remaining parts, 25. 25 is not power of 2. So let's take out another power of 2 out. That's 16. Then 8. Then 1. Okay? After that, we get sum of powers of 2. Okay. But all these power of 2 numbers, we can find monomials with exponents, these power of 2 in our resource pool, right? Yeah. So we can find, monomial power 2 in our resource pool. Yeah, this is our resource pool. Okay. Already available. Okay. Do not recalculate them. Okay. Do not do another round calculation. Then you waste a lot of resource. Okay. Yeah. Now, let's put them together. Okay. This time I write the final round of multiplications. Yeah. The monomial x to the 217 left-hand side equals then. Yeah. First monomial power of 2 monomial x to the 128th. Second monomial with power of 2 exponent, x to the 64. Third, x to the 16th. Next, x to the 8th, then x. Okay? There are 5 monomials, right? 5 monomials. X, given x. Okay? Yeah, we can use it anytime. Okay? Given x. Yeah. If you like, you can put that x in this pool also. Okay? Yeah. It's fine. Yeah. Because its exponent its exponent is 1, right? Right. 1 is also power of 2, right? 2 to the 0, that's 1. Okay? Yeah. So this is also our resource, x. Okay? Yeah. Yeah. All right. So then the last round of multiplications, 5 terms. So we need 4 multiplications in this round. Yeah. In our preparation round, 7 multiplications. Then the next round, 4 more multiplications. The total number of multiplications, 7 plus 4 equals 11. So the final answer, we need 11 multiplications to find x to the 217th monomial. So in this example, you can see how to use this idea, reuse the resource. That's very important. Reuse the resource to save your computation resource as much as you can. Yeah. Yeah. Okay. Yeah. Any question?
So the 7 multiplications came from the largest power of 2 under n, which is 128. You get that by raising 2 to the power of 7. So that's where the 7 came from, right?
Yeah, 7 common. But we do step by step. All right. The first time you calculate 2 squared, you need 1 multiplication. All right. After that, another square operation. So first 1, second, third, fourth, fifth, sixth, seventh. You do the squaring operation all the way. Okay. First square, then 2 to the 7th. Okay, all the way. Yeah. Yeah. 1 at a time. Yeah. That's so. After 7 multiplications, we have this pool of intermediate results. Yeah. Each one is a monomial with exponent power of 2. Yeah. That's our preparation round. Okay. Yeah. And here, yeah, another thing. Yeah. Yeah. Another important view at the structure we are doing here, binary representation. Can some of you connect to binary representation? Because given a decimal integer, this is a decimal integer, right? 217, this is a decimal integer. We can always represent it as the binary representation, right? Yeah. So you know that. In your discrete math, okay, you learn how to convert a decimal integer to a binary integer. Okay? Question?
In the multiplications, would you also count 2 to the 0th, like 2 to 0 and 2 to the 1st as multiplications?
Which round? Preparation round or this round?
Preparation.
Preparation. We don't count. Yeah, 2 to the 0, that's x given. So we don't need a multiplication. Yeah. But here, we put it here, it's our resource, right? So we just put it in this pool. But this one, we don't need a multiplication to get this one, right? Yeah. So this number is given. Yeah. But it's useful, so we put it here, right? The reason we put it here, it's useful, okay? Because here, we need to use that number, okay? Yeah. So its exponent is 2 to the 0, okay? Yeah. All right. Then, so let's still continue our binary representation. Given 217, you can represent it as a binary number, right? Yeah. So here the general process, given a lot, so given n, so we find the largest k such that 2 to the k minus n, okay? Yeah, k multiplications. Yeah. And in this situation, 2 to the k plus 1 must be strictly greater than n, right? Yeah. Because otherwise, 2 to the k won't be the largest power of 2, less than equal to n. Yeah. So 2 to the k plus 1 must be strictly greater than n. Okay, so here, because when we do analysis, we need to use a lot of math, which implies that n less than or equal to 2 to the k plus 1 minus 1. Okay. Yeah. So here the difference is this unequal sign, it's a greater than sign. Here this sign is a less than or equal, containing equal case. But we just minus 1 here. After you minus 1, it's possible to get an equal case. Yeah. So n less than or equal to this number. Yeah. And we know any n less than or equal to this number can be represented as the sum of powers of 2. Because if you add up all the different power of 2 numbers, you get the same number. 1 plus 2 plus 2 squared and so on, plus 2 to the k, you add them up. So this is a geometric series, right? This geometric series equals this number. Do you know that formula? Geometric series. Here, let me review a little bit. To calculate geometric series, 1 plus a squared plus a to the k, okay? Geometric series equals a to the k plus 1 minus 1 over a minus 1. Here a equals 2. So the numerator 2 to the k plus 1 minus 1. Denominator 2 minus 1. A is 2. 2 minus 1 is 1. So denominator is gone. Denominator is 1. It's gone. So we have this equality by this formula. Summation of a geometric series. This formula. Okay? Review a little bit. All right. That means our preparation pool, we collect all the monomials with exponents power of 2 up to less than or equal to the given number n. That pool is enough to represent all the integers less than or equal to n. Less than or equal to n. Our resource pool is enough to represent any positive integers less than or equal to n. Okay? Yeah. So we don't worry. So our resource pool is good enough. Okay? Yeah. All right. So then, how to form x to the n binary representation? There is a relationship. So there is a relationship. You select. But how to select? Okay? How to select? There is a relationship with the binary representation. Because if you represent n as a binary expression, you have 1, 0, 1, 0, right? Okay? 1, 0, 1, 0. A lot of 1, 0 coefficients. At the place 1, you select the corresponding monomial. At place 0, you don't select. Okay? At place 1, you select that corresponding monomial. 0, you don't need it. Okay? It's 0, you skip it. Yeah. So that's the way you select monomials. Yeah. So you can use the binary representation. All right. Yeah. All right.
I have a question. So for A in this case, it's 7, right?
Yes.
And then 2k plus 1 minus 1, would that be like, in this case, it would be 255?
Yes.
Okay. But like, where did you work with number 255?
Yeah, 255. Yeah, good number. So you asked me 255. All right. Here, my conclusion is, look at my statement. If we need to represent any number less than or equal to 255, okay, our resource pool is sufficient. This resource pool is sufficient to represent any number less than or equal to 255. Okay? Use the terms. Use the, terms inside this pool. Okay? For example, 250. 250, we can select certain terms in this pool, put them together, we get 250. Any number less than or equal to 255.
Okay, so that's all that's saying then?
Yeah.
Basically like that's
Right. Yes. Yes. Yeah. Sufficient. So that's what I want to say. Yeah. How much we can do with the pool, right? How much we can do with the resource in the pool. We can represent any monomial with exponent less than or equal to 255. That's the conclusion. That's the conclusion. Okay? Yeah. Yeah, but how to see that? We use geometric series here. Okay? Geometric series. Geometric series here, the largest number we need, we use all the resources in the pools, right? You can see here we use all the terms in the pool. So we get 255. Okay? You don't miss anyone. You use all of them. You get 255. Okay? Yeah. Then when you take away some of the terms, you can represent other smaller numbers. Other smaller numbers. Okay? Yeah. All right. So you can see a lot of things. Yeah. All right. So we finished this topic. Okay? Repeated squaring topic. Then I want to move to next topic, repeated cubing topic. Yeah. Because we have the background. Yes. So here, yeah. We have the background of the repeated squaring. So repeat cubing, we just do the similar things, but we need to modify slightly at a few places. Yeah. The similar idea, but some small differences you need to consider. Okay, all right, so let's, yeah. Why the structure of power of 2 is so special? Okay, yeah. Can we work on the structure of power of 3? Well, we can try it. We can see how much we can do using powers of 3. Yeah. Let's work on the same example and see what result can we get. Yeah. N equals 217. Okay, yeah. Then, similar step. What is the largest power of 3 less than or equal to this number? We need to find that number first. 81. 3 to the 4th, 81. Because 3 to the 5th, 243. It would be greater than this number, n. So we cannot take 3 to the 5th. So we have to take 81, 3 to the 4th first. All right. Next, when we take away 81 from 243, 17, this time, we need to do things slightly different from what we did before. What we did before, we just take away that number power of 2 from n, but here, because it's 3 is different from 2. You need to consider that difference. 3 is different from 2. Okay? Yeah. So in what sense 3 different from 2? When you, for 2 case, when you represent number, decimal integer, as binary representation. For 3 case, you need to represent as ternary representation. Not binary, ternary representation. Base 3 representation. So this time you need to use base 3 representation, not binary, ternary representation. Okay? But in ternary representation, the coefficients could be 0, 1, and 2. Ternary representation. Okay? So here, we do ternary representation. Ternary. Okay? Yeah. Binary, ternary. All right? Yeah, my spelling, yeah. Or that R, yeah, looks weird. Ternary? Yeah. Anyway, all right? So the coefficients, 0, 1, and 2. You can use 2 as the coefficient. Yeah, because base 3, you use base 3. You use base 3. Okay? All right. Then, preparation pool, resource pool. All right? Yeah. How many multiplications do you need to get x to the 81st? 8 multiplications. 8. Let me show you how to use 8 multiplications to get this pool. Yeah. X cubed, we need 2 multiplications. X times x times x. 2 multiplication, not 1, 2. Okay, all right. Next round, x cubed times x cubed times x cubed. So x to the 9th, another 2 multiplications. Then x to the 9th times x to the 9th to the x to the 9th. 2 more. Okay, yeah. And 2 more. Yeah, yeah. So you do 2 multiplications 4 times. So total you need 8 multiplications. Okay, so your resource pool, these monomials. You can use these monomials in your resource pool. Okay. All right. But when you use each monomial, you can use twice, up to twice. Yeah, because the coefficient for the ternary representation, we can use coefficient 2. So each monomial you can use up to 2 times, not 1 times. Our power of 2 monomials, each was up to 1 time. So here, up to 2 times. Okay, all right. Yeah. So let's do the decomposition. Yeah. 217, 81, power of 3, we use twice. 2 times 81. 2 times 81 still less than 217. We can use the coefficient 2 because in our ternary representation, coefficient 2 is allowed. Okay? So here, yeah. If we use x to the 81st twice, still within the bound, right? Within the bound. So we can use it. Okay? Yeah. So the first power of 3 we use twice. So we have 55 left. 55, we need to use power of 3 We also use twice. 27, 2 times 27, 54. Okay, so use that power of 3 twice. Okay, as much as we can, but up to twice. Okay, yeah, so then plus 1. Then plus 1. Okay, yeah. With this decomposition, we can write our last round multiplication. Last round. X to the 81st, x to the 81st twice. Twice. Okay? Yeah. In our multiplication representation, yeah. X to the 27th twice. Also twice. Then x. Yeah. How many more? 1, 2, 3, 4. 4 more multiplications. Okay? Total preparation round, the final calculation round, adding together 8 plus 4, 12 multiplications. If you use this repeated cubing technique, you need 12 multiplications to find this monomial, x to the 217th. One more than our previous method, right? Previous week, 11. This one, 12. One more than that. Okay? So that means for this question, repeated squaring does better than repeated cubing. But just for this example. For other examples, it's possible repeated cubing does better than repeated squaring. Okay? Yeah. For example, let's look at the case when n equals 15. This number, n equals 15. If we do repeated squaring, let's see how many multiplications do we need. First, in our preparation round, in the pool, x squared, x to the 4th, x to the 8th, right? Yeah. So we need 3 multiplications here in this round, preparation round. After that, how to get x to the 15th? X times x squared times x to the 4th times x to the 8th, right? So 3 more, okay? 3 plus 3 equals 6. Okay, all right. That's repeated squaring. How about repeated cubing? Okay, repeated cubing. Okay, all right. Yeah. X right? 4 multiplications, right? Yeah, 4 multiplications. But to get x to the 15th, x to the 15th equals x to the 9th times x to the 3rd times x to the 3rd. 2 more, still 6, still 6. But actually there is a, so this way, yeah, that's interesting. So this way we also get 6, right? Yeah, we also get 6. But let me show you a different way. We can do better than this one. We can do better than this one. Okay, yeah. We can do better, so here, yeah, the way to do better, we mix repeated squaring and repeated cube, mixed way, okay? So we use mixed way. Mixed way. We can do both repeated squaring and repeated cubing. How about that? Okay? So now, 2 parts. The first part, repeated squaring. Repeated squaring. X times x we get x squared. X squared times x squared, we get x to the 4th. Then x fifth equals x times to the x to the 4th, right? How many multiplications we need to get x to the 5th? 1, 2, 3, right? 3, okay? After 3, we'll get x to the 5th, all right? Then, x to the 15, so here, 3 multiplications. X to the 15 equals x to the 5th times x to the 5th times x to the 5th. Here we use repeated cubing. 2 more, right? 2 more. So total 3 plus 2 equals 5. Here you can see, if we can mix repeated squaring and cubing, we can do better. Better. So 5 multiplications. Yeah. Well, how to mix? Yeah. How to use some efficient way to find the mixed way. Yeah. Find the mixed way. So that's an interesting question. You can think about it. Okay? You can think about how to mix repeated squaring and repeated cubing. Yeah. That's an interesting question. Okay? Now, I do not know the answer. I just throw out this question. So I do not know the answer. Okay? Yeah. If you want to think about it, yeah, that's interesting. Later we can discuss about it. Okay? Later we can discuss about it. Yeah. And as I mentioned at the beginning of the semester, if you, because we have two standard projects, and I may give you 2 optional objects. So this topic, I can create an optional project, optional project, if you want to try. How to mix repeated squaring and repeated cubing to get a minimum number of multiplications to calculate monomial. That's the question. Okay? Yeah, that's an interesting question. Yeah. Not very easy, but very interesting. Okay? Very interesting. You can think about it. All right, yeah, I need to move to. So here I finish. Right, so, yeah. So here the question, which method better the conclusion? So look at this question. Which method, repeated squaring or repeated cubing, performs better in general? So the answer, sometimes repeated squaring does better, sometimes repeated cubing does better. Okay? Sometimes the mixed way does better. Right? Yeah, that's the answer. Yeah. All right. If you want to have the more specific answer, if we know when n is a power of 2, then repeated squaring does better. When n is a power of 3, then repeated cubing does better. When n is not power of 2, not power of 3, then sometimes this is better, sometimes that is better. So then, could be very complicated. Okay, the situation could be very complicated. Okay, no quick answer. Okay, yeah. How to mix repeated squaring and repeated cubing? That could be very complicated. Okay, yeah. All right, so we finish C.4, repeated cubing topic. Yeah. Any question?
How did you get 8 multiplications with the x to the 8?
Do you mean here? Is it here?
Yes.
Okay, good. To get x cubed, we need 2 multiplications, right? X cubed. 2 here. Dot. Okay? X to the 9th, 2 here, right?
Okay.
X to the 27, 2 here, right? Then x to the 81st, another 2, right? So 2 4 times. We use 2 multiplications 4 times, total 8. Not 4, not 4, 8. Okay? Yeah. All right? Any other questions? Yeah. Other questions? All right. Then we move to the last topic, 3.5. Take advantage of the structure of Pascal's triangle. So this topic here, we need to use a special structure called a Pascal's triangle. Okay? All right, let's look at the question. Consider a special monomial, non-monomial. This time, we don't want to consider monomial. Okay? Non-monomial. Yeah. All right. Then, this question related to, remember I mentioned that quiz question. Yeah. That quiz question, it's not a monomial. Okay? Not a monomial directly. Why? Because I said the polynomial of degree n with n terms. I said that polynomial of degree n. Oh, I said that polynomial. I don't say degree. What degree? I just said that polynomial has n terms. Okay? Then it cannot be monomial, right? Monomial only one term. Yeah. I said that given polynomial with n terms. So it must be a polynomial. Okay? Yeah. So here, non-monomial polynomial. Okay? All right. But follow some special pattern. Even non-monomial, it could still follow some special pattern. Okay? Yeah. So here I want to talk about the special pattern corresponding to that Pascal's triangle. Yeah. So very famous, interesting structure. Pascal's triangle. Yeah. This one. Yeah. Have you seen triangle like this? Yeah. So we put all the coefficients for binomials. Here we consider non-monomial, but binomial. 2 terms, x plus y, parentheses, raised to nth power. That's binomial. Okay? So here we consider non-monomial, but binomial, x plus y to the nth. So we call it binomial. Okay? Yeah. Do you know binomial formula? The famous binomial formula, also called the Newton's formula. Newton's formula in your discrete math. Here you can see I use a lot of knowledge from discrete math. All right, so here, the famous binomial formula. X plus y, parentheses, to the nth. The formula, we need to use the combinatorial numbers. Yeah, so this, choose n choose 0. Yeah, so this notation, we, if we say that, n choose 0. Yeah. Among n objects, we choose 0. So that number, how many? Yeah. So that combinatorial numbers. That's a combinatorial number. Okay. I will give you a formula. So the coefficient of the first term, coefficient of the second term, n choose 1 among n objects. Each time you just choose one object. Okay? How many times? So that combinatorial number. Okay? I will give you a formula later. Okay? Here I just tell you the notation, meaning of the notation. Next coefficient, n choose 2 among n objects. Each time you choose two different objects in total n objects. How many ways to choose, right? So the combinatorial numbers. Yeah. All right. Yeah, so this is the binomial formula, also called the Newton's formula. Yeah. Newton found it. Okay, all right. Then the definition of this combinatorial number, n choose k. Okay. N choose k equals this number. N factorial over denominator 2 factorials, product of 2 factorials. The first one, k factorial. The second, n minus k factorial. That's the definition of the combinatorial number. N choose K notation. Yeah. Okay, that's the formula. All right. Now, these combinatorial numbers, we can use them to build this Pascal's triangle. Okay? So how to build? Here, let me show you how to build. Yeah. The top level 1, the tip of the triangle 1 corresponds to x plus y parenthesis to the 0. Okay? Power is, exponent is 0, it's 1. Okay? It's 1. Only one term, it's 1. So we put at the top. Next level, 1 corresponds to the coefficients of parenthesis x plus y to the first. To the first. So xy coefficient is 1, 1. Okay? All right. Next level, x plus y parenthesis squared. Square coefficient 1 to 1, right? 1 times x squared times 2x squared plus 2x squared plus y squared. Okay? Coefficient is 1 to 1. Yeah. Next round, x plus y parenthesis to the third, 1, 3, 3, 1. Next row, 1, 4, 6, 4, 1, and so on. Okay? Yeah. All right. So that's, how we get all these coefficients. These coefficients, there is a property. Okay? Each number equals the sum of its shoulder numbers. Yeah. Higher level, 2 shoulder numbers adding together. Yeah? So the 2 shoulder number adding together, so you get the current number. Okay? Yeah. So the structure like this, we call a Pascal's triangle. Okay? All right. Now, after we have this structure, then how many multiplications do we need to calculate this polynomial? Yeah, this polynomial. Okay? Yeah. If we do not consider this special structure, if you just apply Horner's rule, if you just treat it as an ordinary polynomial, you apply Horner's rule, right? Yeah. If you apply Horner's rule, how many multiplications do you need? Can you tell me how many multiplications by Horner's rule? By Horner's rule, how many multiplications do you need? Four. Perfect. 4, not 5. Okay? Not 5. Why not 5? Degree is 5. Okay? But the coefficient of the leading term, yeah, degree 5 term, we call the leading term. The coefficient of leading term is 1. If the coefficient of leading term is 1, you save 1 multiplication. The last multiplication, you do not need to. 1 times, you don't do it, right? 1 times something. Yeah. So the answer is 4 by Horner's rule. Now, the question, can we do better than Horner's rule here? Can we do better than Horner's rule with a fewer number of multiplications? Think about it. Can we do better than fewer than 4 multiplications? Can we do in fewer than 4 multiplications? Yeah. Yeah. Some magical way. Yeah. Yeah. Pascal.
Is it 4 multiplications because, nx squared has 1 and nx equals 3?
Horner's. Remember that parenthesis formula, factorization? Remember that formula, factorization? Nested factorization? You need to go back to that one, nested factorization. Okay? Use that formula. Do not try to, because many students try to think about how do I, you cannot use 4, right? Because it's hard to use 4. But if you go back to our Horner's rule, we have a formula for Horner's rule. Okay? If we look at a formula for the Horner's rule, it's easy to see 4 multiplications. Because that formula, many people cannot see it. If you have it, then it's very powerful. That formula is important. Okay? If you forget that formula, then even use 10 multiplication, you may not be able to get this one. Okay? Yeah. All right? So that formula, important. Yeah. Because when I did grading, I noticed many students didn't know that formula. Horner's rule formula. Okay? All right. Yeah. So here, Pascal's triangle. Yeah. Can you use Pascal's triangle to save a little bit on multiplications? Yeah. Because if you look at the coefficient, the numbers, is it the same as this line, this row? Exactly the same, right? In Pascal's triangle. That means this polynomial corresponds to binomial. What binomial? Corresponds to a binomial. Okay? Yeah. So Horner's rule 4 multiplications, but based on the Pascal's triangle, we get this binomial, x plus 1 parenthesis to the 5th. This binomial equals the given polynomial, right? Can you see that? The binomial. Y equals 1. Okay? Y equals 1. Then the coefficients from Pascal's triangle. X plus 1 parenthesis raised to 5th by repeated squaring. How many multiplication? Because this one, parenthesis, inside parenthesis is an addition. Can we treat that whole parenthesis as one number? Then you have a monomial, right? Parenthesis to the 5th, you treat it as a monomial calculation. When you calculate monomial x to the 5th, how many multiplications do you need? First one, x plus 1 times x plus 1. Squaring, 1 multiplication. Next one, x plus 1 square times x plus 1 square, second square operation, squaring, x plus 1 to the 4th, second multiplication. The last one, x plus 1 to the 4th times x plus 1, parenthesis, x to the 5th plus 1 to the 5th, third multiplication. So you need 3 multiplications to find this binomial. So your final answer, you just need 3 multiplications. Better than Horner's rule 4 multiplications, right? Huh? All right? Yeah. The reason we take advantage of special structure, Pascal's triangle structure. Okay? Yeah. So in our homework number 1, yeah, so after a few weeks, yeah, so we need to build up. Yeah, we need to build up. So after a few weeks, when I give you homework number 1, you may have some question. Yeah, could be in quizzes, could be in our next quiz or homework assignment. You will have some question using Pascal's triangle. Pascal's triangle. Okay? Yeah. All right. Yeah. So we finish this topic. Okay? All right. Yeah. So then we have less than 10 minutes. Let me just do a little bit part D. Yeah. Definitely I cannot complete part D.1. but let me just do one slide, okay? One slide, D.1. Topic. So this is another important topic in algorithms, part D. Optimality of algorithms. After we get an algorithm, sometimes, not always, sometimes, we want to look at if our algorithm is optimal or not. Optimal or not. So that is already the best you can get, right? If it's optimal, that means you cannot improve it. Already optimal, okay? Yeah, you cannot improve it. Yeah. D.1, minimum selection problem. Minimum selection problem. So this time, our problem number 3, find the minimum of an array. Question, given an array, capital A, with indices from 0 through n-1. Question, find the index I such that A of I is the minimum of the array. Okay. This is of our new question type. So this type we call a selection type question. Okay, selection type. Remember 3 basic types. Search, sort, selection. So we did a search one, and then we did this time selection one, next time sort one, basic type. The reference I'll give you here, okay? All right. Selection problem. First, let me explain the general selection problem. So this one is a special selection problem. The general selection problem is like this. Find the kth smallest element in a given array. A. Kth smallest. K is known. All questions like this, we call a selection problem. Okay? Yeah. For the minimum question, K equals 1. Minimum, it's a special case. When K equals 1, finding the minimum. Maximum, when K equals n, that's the maximum problem. Okay? Yeah. All right. Yeah. So let's do some analysis here. Yeah. Solving this problem is quite easy. I think everyone here, you can write a program to find the minimum easily. Right? Yeah. So finding the solution is not hard. Okay? The hard part is we want to look at the optimality part. That's hard. The optimality question is hard. Okay? All right, so here, yeah. So let me quickly go through this, the solution. Yeah. Then we discuss the optimality. Yeah. First, we do initialization. When we start, we initialize our variable, the min variable. We want to use this variable to store the current minimum. Okay? Yeah. At the beginning, the current minimum is the value of the first element, A of 0. A of 0. Okay? Yeah. At the beginning, when we start. Yeah. The general step, every time we compare the value stored in this main variable with current element, A of I. A of I is a current element. Okay? So we go through all the elements in the array in natural order. Yeah. So each time the current element, we compare it with this value stored in this main variable. There are 2 cases we can consider. The first case, when main strictly greater than A of I, we replace the older value in main by the current value in A of I, current value. Okay? So we make it smaller. we make the current minimum smaller in this variable. All right. Otherwise, that means min less than or equal to a or y. We don't update. Okay, we don't update. So we move to the next iteration. Yeah. Then another round comparison. Yeah. Until we reach the end. After you reach the end, after you finish comparison with the last element in the array, then that main variable should store the global minimum. Okay? The minimum of the whole array. So that's the global minimum. So that's your final answer. Final answer. Okay? Yeah. Yeah. Let's count the number of comparisons. So for this simple algorithm, can you tell me how many comparisons we need to do here? Counting. Another counting, simple counting question. Good. Any other question? First one, n comparisons. Any other questions? Other question? N minus 1. Yeah. N minus 1. And yeah, there is one difference. In this situation, how to get correct answer? N minus 1 n. Yeah. All right, so here, yeah, because we do not have a lot of time, yeah, only 2 minutes left. Here, we apply counting by reference, that method. Okay? Find the reference, appropriate reference objects. Array elements, we can use array elements as reference, right? For the first array element, we do not do comparison, right? We do assignment. For the first element, this is assignment. This is not comparison. We don't count assignment. Okay? We only count comparison. So the first element, there is no comparison. So we don't include it. Okay? Yeah. So then, starting from element with index 1, we count it. Okay? There is one comparison. Index 2, 3, 4. Yeah. So the elements with indices from 1 through n minus 1, we have one-to-one correspondence with comparisons, right? One-to-one correspondence. But not 0. 0, no comparison. Okay? For that reason, so we have n minus 1 comparisons, not n. Okay? Yeah. Counting by reference. Yeah. All right. Yeah. So we finish this slide. Next time we discuss the optimality. Okay? That's important. Optimal or not. That's important.